I hope everyone's doing well today. I am Mr. Ish. Thank you for joining me for this video where we are looking here at yet another facet of derivatives. We've looked recently at approximate value calculations, square roots, different types of roots, and trigonometric. But here we're looking at approximate change calculations. What is an approximate change? We will be focusing here at the dy, which represents your approximate change. But how does this dy come about? You have a particular function, y is equal to a certain item. Let's just call it f of x. You do the derivative and the dy comes about. Dy over dx is equal to the derivative here. Solve for dy. Dy is equal to, you push this over here, you have dx, your derivative of your function. This right here represents your approximate change, but you have to contrast this with actual change. And we will look at both. It is just another facet of derivatives and it's an interesting application. Let's look here at an example. We have a function here, y is equal to x squared plus x plus 1. The value of x changes from a 3 to a 3.01. What is your approximate change? And for the purposes of this video, what is the actual change? Let's look here at the actual change. You know what you're looking here at is you have an x value 3.01, then you have an x value 3. If you were to look over here at f of 3.01, and then you were to minus f of 3, you're going to get here your actual change. Because you're putting in one value, the new value, and you're putting the original value, and what is the difference of the two? That's your actual change. That's a simple concept, but we also have to look here at the approximate change using derivatives. Look here at this. I'm doing f of 3.01. I'll have 3.01 square plus 3.01 plus 1. This is f of 3.01 minus f of 3. Now I'll put 3 in these. I have 3 square plus 3 plus 1. What is the actual change? Let's determine it by bringing out our calculator. Let's look right here at this part. We do 3.01 square plus 3.01 plus 1 minus these set of values, 9 plus 3 plus 1, which is a 13. I'm minusing 13. I have a 0.0701. That's my actual change. My actual change over here, I'll just symbolize this as actual AC is equal to a 0.0701. The determination of actual change is easy. The determination of the approximate change requires you to bring in the derivative calculation. How do you do the approximate change? I told you have to focus here on the dy. If y is equal to this, your dy over dx brings in the derivative. What do I have over here? I have a 2x plus a 1, derivative of a constant is 0. Solve for dy is equal to dx times 2x plus 1. Now I need to find what x is and dx is. And how can I do that? X is your standard value 3. X here is your standard value 3 because you're making a change from 3 to something else. The original item is your x value. What's your dx? Your dx is equal to your delta x, the difference between the two. What are you going from 3 to 3.01? What is your difference? You have one value x, which is 3, the other one 3.01. You're going from here to here. What is it? What's your delta x? Is 0.01. That's what it is, 0.01. You bring in these items and you plug them here into this. You have a dy, which is your approximate change. No longer your actual change, but your approximate change is equal to 0.01 times 2 times 3 plus 1. What are you going to get over here? You have 2 times 3 is 6 plus 1 times 0.01. You'll have a 0.07. This right here is my approximate change, APC. And my actual change is 0.0701. My approximate change is 0.07. Obviously, this is the most accurate, but this is close enough and it's considered good. It's accurate as well. It's not 100% accurate, but it's an approximate change, and you can use derivatives to determine an approximate change. Look over here at this second example. We have a function y is equal to 1 over x. What is the approximate change if x were to change from 1 to 0.98? These apply derivatives because you have rates of change coming. Based on those rates of change, your approximate change can be either stark or drastic, or it can be not so drastic. If you had a function which is like an x cube, which looks like this, if you're going from one x value to another x value, you can have a significant change in terms of the slope of your tangent line. Here the slope is not as steep, but the minute you change it on an x cube type of function, your change becomes rather stark or drastic. If you have a function which is like 1 over x, which is something like this, you're going from one x value to another x value. Here you have a certain derivative applying horizontal. Here you have another, and let's make another change to this other. As this graph is flattening out, the change is becoming less and less. Your approximate change becomes less because your graph is leveling out. The rate of change is coming into play. What we're looking here at is a 1 over x, which would look something like this. So let's keep the derivatives, the slopes of tangent lines in mind as we're looking at something like this, because the slope of such a curve will impact at a particular point your rate of change, or your change may not be as big or as small as you would expect. When I'm looking at this, what's my actual change? Your actual change calculation is easy. You're going from 1 to 1.98. You're doing your new value minus your old value. You'll do 1 over 0.98 minus 1 over 1. Because the function is 1 over x, you're going from an x of 1 to 0.98, my new value to your old value. The difference of those will give you your actual change. So we are doing this, and it's easy. You'll do 1 divided by 0.98 minus 1. My actual change is all of this, 0.020408.163. Let's write it out. And I've written it out for you. That's your actual change. But what about your approximate change? This right here is your function. You're doing the derivative dy over dx is equal to the derivative of 1 over x. You know this is x to the power of minus 1. Bring in the power rule. I have minus 1 over x squared. Solve for dy is equal to minus dx over x squared. This right here is my dy. This is going to give me my approximate change. But I need to have the value of dx and x. I know what my value of x is. It's your standard value, which is your x equals 1. That's my x, which will come right over here. What's my dx? Well, dx is going to come from your delta x. You're going from 1 to 0.98. What is that going to be? You're going from 1 to 0.98. That's a minus 0.02. Because to go from 1, you have to minus 0.02 to get 0.98. That's your delta x. You plug in these items over here. I have dy is equal to, you have a minus, dx is a minus 0.02 divided by 1 square. When you compute all of this, the minuses cancel out. You have a 0.02 divided by 1. It's equal to a 0.02. My approximate change is a 0.02, but my actual change is quite significantly more precise. But you can see 0.02, 0.02, you still see it. Here you're seeing an approximate change calculation come out by means of derivatives, and it's not bad. You're only differing by these, but they're kind of negligible. 0.02, 0.02, it's good. I would say it's square and it's dead on in terms of a acceptable range of value we're looking at. The approximate change over here should be good, very close enough to actual change. Let's look over here at a bit of a more practical example. We have a circular plate made of a certain material which is able to absorb heat. It expands due to heat. It undergoes heat expansion. The radius changes from 5 to 5.06 inches. We have to calculate the approximate change in the area. And that's what we're focusing here on, the area. You know it's a circle. And how do we do it? We're focusing on approximate change. We will do it. We have a certain formula over here. You know circle area is equal to pi r square. We are looking here at area is equal to pi r square. If I were to do the derivative of this, I'm looking at dA or dr. The area and the radius variable is equal to the derivative of this. You have a 2 pi r. Now how can I calculate the approximate change of the area? You'll do the solving for the dA, the area derivative, the area variable differential. That's what you're looking at, is equal to dr 2 pi r. Now you bring in your values. You need to know only dr and r. We can easily determine dr. Your dr is always equal to your delta x, but here you can say delta r. You're going from 5 to 5.6, it's an increase of 0.06. But what is my r value? It's your standard value, 5. Bring in these items. You have here a 0.06 times 2 times pi times radius, which is a 5. What is the end result? That will give you your approximate change in the area. You can also call it an approximate increase in the area. Let's do the calculation. 2 times pi times 0.06 times 5. I have a value here, 1.8849. I'll round it up to 1.885. 1.885, and I'll say inches, and I'll say inches square. This right here is a symbol for inches. Inches square. We can just put here in and square and look even better. And that right there would be the end result. If you were to do an actual change, you can just run this value to the area formula, run this to the area formula, do the difference, you'll get your actual change, but the approximate change will be very much close to that. And that right there is the end of this video. Thank you for watching.